Alright, in this video we're going to look at our final shortcut rule from the initial batch of derivative rules that we're going to learn, and a few other examples related to these rules. So we start with rule number 7, the power rule for negative integer powers of x, and you should notice that this is identical to the power rule for positive integer powers of x, except for we now are saying n can be a negative integer. So why do we have this whole new rule when we already have a power rule for positive integer powers of x? Well, the proof for the power rule that we first did relied on n being a positive integer, and so we're not necessarily sure that it works for negative integers, and so we're going to prove it. And later on we'll find that the power rule works for any real number, and we won't prove it for cases beyond the integers, but I wanted to show you this proof because I find it interesting. So we are going to suppose that n is a negative integer, and x does not equal 0. And then we are going to, I guess I should have put n in there, suppose n is a negative integer. We're going to let m be equal to the opposite of n, so m is a positive integer. Then the derivative with respect to x of x to the n is equal to the derivative with respect to x of x to the negative m, which is equal to the derivative with respect to x of 1 over x to the n. And now we can use the quotient rule to evaluate this. We've got low times the derivative of high minus high times the derivative of low. And we can apply the power rule to that since m is a positive integer, all over the denominator squared. Simplifying this, we get negative m x to the m minus 1 over x to the 2m. Using exponent properties, this is negative m times x to the m minus 1 minus 2m, which is equal to negative m times x to the negative m minus 1. But since m equals negative n, comma, n is equal to negative m, so this is, I'm just going to replace the negative m's with n's, n x to n minus 1. And we're done. There's the proof of the power rule for negative integers. Alright, let's do some examples using this. Alright, y equals x to the negative 3. So dy dx is equal to negative 3x to the negative 4, which I could also write, if I wanted to, as negative 3 over x to the 4. Right, either one of those would be acceptable in this case. Alright, and now in part B we're doing y equals 3 over x to the 4th. Well, in order to do this problem, instead of using the quotient rule, I'm going to, since I just have a single term in both the numerator and the denominator, I'm going to bring that x up and make the exponent negative. And now I can apply the power rule for negative integers. And so dy dx is equal to negative 12 x to the negative 5. And in this case, I do want to rewrite it this way since it was written as a fraction originally. I'm going to write it as a fraction in my answer. And there's my derivative of 3 over x to the 4th. Alright, in this last example we're going to do some generalized things where we know the values of these two functions and their derivatives at a specific point. and we're going to find the values of these derivatives at x equals negative 2. So first of all, part A, the derivative with respect to x of u times v. So from the product rule, this is equal to u times the derivative of v plus v times the derivative of u. And so if I'm finding this value at x equals negative 2, that's going to be u of negative 2 times v prime of negative 2 plus v of negative 2 times u prime of negative 2. And now all of those values are listed here. And we're just going to substitute the appropriate values in to find the value of this. And so u of negative 2 is 3. V prime of negative 2 is negative 5. V of negative 2 is negative 4. U prime of negative 2 is 2. And we calculate this value and find that it's negative 23. Alright, part B. We're now going to use the quotient rule. And so we've got low times the derivative of high minus high times the derivative of low all over low squared. And since we're finding it at negative 2, that means I want v of negative 2 times u prime of negative 2 minus u of negative 2 times v prime of negative 2 all over v of negative 2 on v squared. And now I can just go ahead and substitute the values in here. And so v of negative 2 is negative 4, v prime is 2, u is 3, v prime is negative 5, v is negative 4, and we end up with negative 8 plus 15, or 7, over negative 4 squared. And there's the value of the derivative of u over v, given this information. Now the derivative of v over u, same concept, except different order here. So now we've got u times v prime minus v times u prime all over u squared. And so we've got u of negative 2 times v prime times v prime of negative 2 minus v of negative 2 times u prime of negative 2 all over u of negative 2, the quantity squared. And then I need to substitute all of those values in. Alright. U of negative 2 is negative 3. V prime of negative 2 is negative 5. V of negative 2 is negative 4. U prime is positive 2. And u of negative 2 is negative 3. And doing all the calculations here, I've got 15 plus 8, which is going to give me wait a second. It's not negative 3, it's positive 3. Right? U of negative 2 is positive 3. That's what I get for trying to remember the values instead of looking up and referencing them. We've got negative 15 plus 8 is negative 7 over 3 squared, which is 9. And the last example, the derivative of 5u minus 3v plus 4uv. That's going to be 5 times u prime of negative 2 minus 3 times v prime of negative 2 plus 4 times uv prime, which I found earlier, and so I'm just going to use that value in here. And so u prime of negative 2 is 2, and v prime of negative 2 is negative 5, and uv prime we got in part A, that's negative 23. And so this is 10 plus 15 minus 92 should be negative 67. Hopefully I did all my calculations correctly in there. But there are a few examples of how we can find generalized derivative values when we only know information about how it behaves at a specific point. We can still find these derivatives using our shortcut rules. Alright, that's the end of our basic shortcut rules videos, and see you next time when we start learning some more things about how we find derivatives.